Hello there. Welcome to our today's science lesson. The topic for the day being a review of the previous topics we have covered recently, and that is the periodic table and chemical symbols and formulas. You remember that we talked so much about the chemical symbols and formulas, how symbols of various elements came into being, the various scientists who did their work to come up with those symbols, and even some of the rules that were used in assigning symbols for those particular elements. We further went to how the symbols of now compounds came into being, how you can name a compound, the rules you are supposed to follow to name a compound. And we even saw that compounds are not just compounds. We have compounds that have only two elements in them, and we also have others that have more than two elements in them. We saw that there are also compounds that have one element but more than one atom in them. So all those form compounds, and all in all, whether it's a compound or an element, you will be talking about a symbol of that particular substance you are talking about, whether it's an element or a compound. After that, we looked at the periodic table, which I said that is a very important component in our life as scientists. For us to understand the so many things that we always talk about, the so many things we always use, the so many things we are trying to make all around the world, the periodic table must be understood. Understood in the sense that you have to understand the properties of each of those elements all the scientists will be using. So we want to make a review of all those areas as a test. All those areas as a test. I will be giving out questions, then go through very fast, and immediately after, around a few seconds after you have reviewed and given your answer, I will give out mine and we compare. You compare if you have done it well or not. So I will have questions on the periodic table, questions on the symbols and formulas, and even the formulas will be in terms of the element, molecules, compounds of the two elements, and compounds with more than two elements. So I will start off with the most recent, and that is questions pertaining the periodic table. The first question, and here I'm going to give 4 responses, and out of the 4 responses, you give the correct one, and it will be always good to give a reason why you have given that as the best response out of the 4 I would have given. So let's start off with the first question, and the question reads, how many protons are in the nucleus of each atom of copper? So the question is about how many protons, that is a number of protons that are present in each atom of copper. So protons in an atom of copper. How many protons are in an atom of copper? And the responses are, we have A, 6, B, we have 20, C, we have 29, and D, we have 55. Since this is an open exam or an open question, you are free to refer. If you have a copy of the periodic table, the better. You can check on the periodic table. But the question is, how many protons are in the nucleus of each of the atom? Now, going back to my periodic table, it's good we know how to get those answers from this periodic table. In the periodic table, you just look for where copper is found. First of all, you have to know the symbol of copper. So knowing the symbol of copper, I have to look for copper where it is, and I get it to be at this point. Copper is at this point. Now the question is, how many protons are in an atom of copper? After finding where copper is, I check on the atomic number. So you check on the atomic number. From the atomic number, one can get the number of protons. How? The atomic number of any element is always given by the number of protons in that particular element. So the answer here, being that it is at atomic number 29, atomic number here is 29, then it automatically qualifies that the number of protons are 29, giving C as the correct response. C is the correct response because the atomic number is 29, which is the same as the number of protons in the nucleus of that particular atom called copper. The second question, which element has 36 protons in the nucleus of atoms? Which element has 36 protons? Which element has 36 protons? So an element that has 36 protons. So it is almost the opposite of the first question we just looked at. The first question, we had to start with the atomic number to get the protons. But in this one, we are now starting with the protons to get now the atomic number, because from the atomic number, we shall now know which element is this. So the element that has 36 protons, you can check on the periodic table, but you cannot know by using the number 36 as protons. You have to use 36 as a different thing, and that is as an atomic number. You can further use this atomic number, which is the same as the number of protons, to now know number of electrons, which will now assist you to identify the locality of this element. To identify the locality of this element. And how do we get it? So from these electrons, we can now get the electronic configuration. Electronic configuration, which will be 2, 8, that is 10, 8, 18, 18, total gives us 36, and that is the end. So if you make a total of these electrons, 2 plus 8, 10, 10 plus 8, 18, 18 plus 18 gives us 36. It has given us an equal number to the number of electrons, meaning that this is the correct electronic configuration. Now from here, we can now get the position of this element by checking on how many orbits. These are 1, 2, 3, 4 orbits, and the outermost, it will go 18 steps, or group number 18. So we start 1, 2, 3, 4. This is the place. I go 18 steps, or checking on the one that has outermost energy level having 18 electrons, and that is the last one. We can confirm that by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And the element is krypton. The element is krypton. So it's good you know all these steps to identify an element. You don't just go to the periodic table, look for 36 and you identify it. No, it will not be good, because you will not be helping yourself. To help yourself, you have to go through all these steps to show that you have really understood. Get the protons, know what it means. It means it's the atomic number, which is the same as the number of electrons, And from the electrons, you get the electronic configuration. You write the electronic configuration. From the configuration, you know now the number of energy levels. From the energy levels, you will know which row to pick on. Then from the outermost number of electrons, you will know which group. So the options that had been given was krypton, potassium, sulfur, and xenon. So automatically it gives us krypton as the answer from the so many that we had: potassium, sulfur, and xenon. Let's look at another question to do the periodic table. What is the atomic number of the element with the symbol Na? What is the atomic number? The atomic number of an element with the symbol Na. Atomic number of an element with the symbol Na. Now this one is linking the periodic table to other issues to do with the symbols of elements. You can only get the correct response to this if truly you know the symbols of an element, and that is you understood when we were talking about symbols and chemical formulas. So the options you are having here are: what is the atomic number of the element with the symbol Na? 10, 11, have 10, 11, 28, and 86. 28, 86. So this one is A, B, C, and D. So the first thing you have to do here is, first of all, know the name of the symbol. This is the symbol. The name is sodium. It's good that way. We know it as sodium. Then from there, if you know other details to do with the sodium, you can use that. If you don't know, then you will have to use the crude way of just looking for an element that is written with that format. But if you know others details, like how many protons, how many electrons, therefore you will get the electronic configuration. And since I believe that you must be having this knowledge, we can now get the atomic number by using that format of, let's identify the number of protons. So protons are 11. Electrons are therefore 11, meaning that electronic configuration is 2, 8, 1, total 11. From here, rows 3. 1, 2, 3. I get to number 3. Then outermost is 1. So this is the place. And I discover it is written atomic number 11, giving B as the correct response. As much as you can get it directly this way, but as I've said earlier, we have also to know all these steps, because they will always show you that you have really mastered the concept of identifying atomic number, or the number of protons, or the position of the element, or even the formula of the element. One more question on the periodic table, and the question reads: which metal is a liquid at room temperature? Which metal is liquid at room temperature? Now this is a question touching on the periodic table, but it also touches on what we talked about previously. This is a metal, but it has another characteristic, and the characteristic is at room temperature it is supposed to exist as a liquid. A metal, liquid at room temperature. Liquid at room temperature. So first of all, we have to check on the metal side. This periodic table is categorized into metals and nonmetals. And we also have the noble gases. Among the metals, we have the alkali metals, alkaline earth metals, and the transitional metals or elements. So, checking on the history of the metals as we talked about them in our previous lessons, we discovered that most metals are solids. Most metals are solids at room temperature. However, the unique one, may I give the response so that we can get it from there? We have bromine, carbon, mercury, and lastly we have water. This one is A, B, C, and D. So, to get the answer out of this, you always need also to know something to do with the other responses. For you to get always the correct response, you need to know or understand what the other response is all about, so that it doesn't bring in much confusion. And why I'm saying that is because of our response number A. Generally, if you cross through them, you'll discover that this one is not a metal, carbon is not a metal, water is not a metal. So it's like we automatically get left with the C as the correct response, mercury. But as I've said, we also need to understand something to do with the other responses. Bromine. Bromine is a confusing part here. It is a confusing part because this is the only nonmetal that will exist as a liquid under normal conditions. Is a nonmetal, but will be existing as a liquid. And here the question is asking a metal that is a liquid. So you can see it is confusing. It is not a nonmetal we are looking for, it is a metal we are looking for. Carbon is a nonmetal, but existing in solid state. Carbon is a nonmetal, but existing in a solid state. And yet, if you look at most of the nonmetals, they exist as gases. So it's also a unique factor. And water here is a liquid. We all know that water is mainly found in liquid form, but it is not even a metal. Neither is it a nonmetal. It's a compound. It's a combination of oxygen and hydrogen. But the confusing part why water is taken as an option is because it's the common liquid we know around. One other question that has a connection with all the others we have been talking about is now in relation to the bromine. Let's look at this question. What is the atomic number of a nonmetal which is a liquid at room temperature? A nonmetal. So the question is mutating to nonmetal, now not a metal, and this nonmetal should be a liquid at room temperature, a nonmetal that is liquid at room temperature. But now we are not looking for its name. The question is asking us to get the atomic number. Atomic number. The options we are having are 9, 17, 35, and 53. A, B, C, and D. Now to answer this question, just like the first one, the previous one I've just looked at, if you cannot understand the science about the states of matter under which metals and nonmetals exist, the various metals and nonmetals exist, you cannot be able to answer this question. You need to understand or to know that these metals exist in solid, but this one does not. It only exists in liquid state. These nonmetals exist in a solid state. This one, gas state, and this one in liquid state. Without that knowledge, you may not be able to get this. So, just an overview of that information. We say that most of the metals exist in a solid state. Name the aluminium, iron, magnesium, they are solid state, in solid state at room temperature or normal conditions. However, we have just seen mercury exists in a liquid state under normal conditions or under room temperature. For nanometals, most of the nanometals exist in a gas state under room conditions. This is why this is because they always combine to be diatomic, or there are always more than one atom. They mostly form diatomic molecules, which because of the weak forces that hold the molecules together, they are always found in a gaseous state. However, we also have those that exist in solid state. A good example being carbon that we have just seen. Another one is sulfur and phosphorus, just to name those ones. But there are just a few that are solid at room temperature. But we have a unique one, the only one, and that is bromine. Bromine is an element which is a nanometal, but when it comes to existence, it is a liquid at room temperature. Having known that now the element we are looking for is bromine, the next story will be to look for any information to do with the bromine. The question is atomic number. If you know the number of protons of bromine, then there you are. The number of the protons are the same as the atomic number. Now that we have identified the element as bromine, if you don't have any other basic information on how to get the atomic number of bromine, we can do it the crude way. Follow up the periodic table. You cannot check now among the metals. You know it is among the nanometals. So among the nanometals you can check and you can get it to be here. Here it is. The atomic number here is 35 and giving us our correct response to be C. But remember, for you to arrive at that 35, you need to have known all the basic information on categorizing metals in terms of state symbols, categorizing nanometals in terms of state symbols, for you to arrive on bromine as the element that exists as a liquid at room temperature. Another question here, now it is moving away from the periodic table, but still it may have an attachment to the periodic table in one way or another. And the question reads, what is the smallest unit of an element? What is the smallest unit of an element? Remember, in the periodic table we are talking about elements, arranging them in order, what Mendeleev stated. But now, what is the smallest unit of this element? The responses we have here are atom. Is the atom the smallest unit of an element? Another one is electron. Is it an electron? Another one is neutron. Is it maybe a neutron, which was discovered by James Chadwick in 1932, when he had to explain why the masses are not just the protons, but is a protons plus neutron, that is 1932, or is it a proton, which is the smallest unit of an element? I'm sure in some ways this can be a bit confusing, because the smallest unit of an element is the whole sum, smallest unit, not subunit, is the whole sum smallest unit, and the smallest unit of an element is an atom. Remember, an atom is a wholesome ingredient that makes an element. But when you look at these other three, they are confusing in the sense that they are subatomic particles. Subatomic particles. Particles that when you put together is when they will form an atom, which is now the smallest unit of an element. The two, neutron and proton, they form the nucleus, and around the nucleus we shall have the electrons, which all together form an atom, which is now the smallest unit of an element. So hope you get that very clearly, and that's why I came in with that question, so that it can clarify on the issue of which one is the smallest particle or unit of an element. The next question is to do with the periodic table. In which region will you find non-metallic elements? So if you are to be given this periodic table without these elements written in it, they have just given colors. And the question you get is, in which region will you find non-metallic elements? From the question here, these two are grouped together. Then the blue region is also same color. Then we have this region, and the yellow and this. Yellow and the green part is one region, and the other one is a different color. Now the question is, in which region will you find non-metallic elements? Non-metallic elements are always towards the right-hand side of the periodic table. But remember, we have unique non-metals, and that is the ones that are found at the edge, the further end. These are noble gases. They are non-metals because they show characteristics of non-metals, but they are never called non-metals. They are noble gases because of their unique nature of being unreactive. Non-metals, on the other hand, are those that show the opposite characteristics of metals, but they are reactive. Show opposite characteristics of metals, but they are reactive. And these are the non-metal, or this the non-metal region. The green ones plus the yellow part gives the non-metal region. So in the options, you will always get the part that will be giving that area as the non-metals. The other question is about periodic table, but also in line with the others. What name is given to the group of elements listed in the table above? So in this table, as I had given, we have the table which is showing these regions. So these elements are in this area. So we have helium, neon, argon, krypton, xenon, and radon. Now the question is asking, at this point we have a zigzag to show this is the non-metal part we were talking about. That's the non-metal part. But now the present question is talking about these elements. So the question is asking, what name is given to the group of elements listed in the table above? What name is given to these elements? It is good to understand that all these groups in the periodic table have names, and these names are assigned based on the similarities in terms of chemical properties. So these elements have the same chemical properties, that's why they are in the same group. And the name to that group, with the options, we have one, because I know some also get confused with that, how best to call them. So let me get the options, and we look at the options. The inactive gases, A is the inactive gases, B the inert gases, C the helium gases, and D, we have the non-metallic gases. Now, looking at the four responses, they are all confusing. If you are not so keen, they can all be correct, depending on how you interpret it. So we have to go for the correct interpretation by knowing the meaning of the other interpretation. Starting with the A, the inactive gases. Looking at the word inactive and looking at where they are located, I'm sure you can still remember we said that those elements that are put at that position, they don't undergo reaction because their outermost orbit or energy level is full. It's just like a satisfied person. Once you are satisfied, the best you can do is even to doze around, because you don't have to be active maybe to look for the food. You don't need to go to the cafeteria to get that food. When you are going, it means you are reacting. You are active. You are reacting. But now here you are full. Do you need to go there? You don't. You will remain where you are, and if you have to take a nap, you can take it. So they are inactive. But is it the correct way of calling them? That's why I said it's a bit sensitive here. You have to use the correct wording when calling these chemical families or chemical groups. Use the correct name. You remember I also mentioned something to do with the group 1 and group 2. Alkali metals and alkaline earth metals. Very specific. So here, going by this, it is not the correct way we address them. So this one cancels A as the correct response. Let's look at response D. The non-metallic gases. The non-metallic gases. It is true. They are not metals. Metals are found on the left part of the periodic table. They are found on the farthest part of the periodic table. So they qualify to be non-metals. And here it is being called non-metallic gases. Is it true that there are gases? Yes. So you can see they are non-metallic and there are gases. But could this be the correct response? No. Why? Because we also have other gases that are not found here that are non-metallic. A good example is what we shall find at this point, and this is the halogens. We have chlorine gas, we have fluorine gas. Are they in the same category? No. We also have gases like nitrogen gas, which will be found here. We shall also find oxygen gas, which is found there. Do they exist in the same category or in the same group? The answer is no. So because of that, that we also have other gases that are non-metallic, and there are gases which are not in the same group, the response is wrong. In addition, being non-metallic is not enough. It should be non-metallic and unreactive. Here in the statement, we are not seeing that part of being unreactive. So it even further qualifies the statement to be wrong. Let's look at response C. Response C is the helium gases. Helium gases. If you look at the elements there, you can see the first element here is helium. So the response C has only picked out one of the so many that have been listed, and that cannot be a representative. It is not asking for a representative. We are asking all the elements. If it were a representative, then maybe it could be correct. But here we are asking the name to all the elements. So on that ground, though it is among them, but the question does not ask for that particular answer. So it leaves out B as the correct response. Why? Because it is having the word inert. Inert means unreactive, just like this one, inactive. But why is it correct and not this one? Because it is taking into account the correct name that was assigned when the chemical families or chemical groups were being given names. The name that is correctly given is inert gases and not inactive gases. Moving on, we look at another question. This one is to do with what we talked about in the previous topics, just before looking at the periodic table. And the question is, which element is a good conductor of heat and electricity? Which element is a good conductor of heat? So, conductor of heat and electricity. So, the element must be a good conductor of heat and electricity. Maybe before I give out the response, to answer this question, you need to go back to the scientific facts we learned about elements. And we categorized elements in terms of properties, and we saw that metals are the ones that do the conducting of heat and electricity. Non-metals do not conduct heat and electricity. However, we discovered that there is an nanometal by the name carbon. There's an nanometal by the name carbon that is able to conduct electricity as graphite. When you have carbon as graphite, it will be able to conduct electricity. But here we are being asked to conduct heat and electricity. Let's see the responses, and from there we disqualify the others as we qualify only one. So the responses are, which elements are good conductors of heat and electricity? We have iodine, hydrogen, magnesium, and oxygen. Then we have lastly oxygen, A, B, C, and D. So as I've just stated up here, after knowing the facts about metals and nonmetals in terms of conductivity, it can be very easy to rule out or rule in whatever is correct. Looking at iodine, iodine, to classify this is a nanometal. Being a nanometal, how does it exist? Under room conditions, is a solid. But even if it's a solid, does it conduct heat and electricity? You will find out that it doesn't, because the only nanometal we saw to be able to conduct electricity is carbon, and not iodine, sulfur, and phosphorus. So A is out. B, hydrogen. Hydrogen, this is a nanometal that has both characteristics of metal and nonmetal, and even if it has some characteristics of metals, it doesn't, in the characteristic or the properties do not include those of conducting heat and electricity. Remember, the confusing part to do with the hydrogen is hydrogen has both non-metallic properties and metallic properties. Some of the metallic properties are, it should be able to conduct heat and electricity. However, to do with the hydrogen, it doesn't share in that. It shares in others, but it doesn't share in being able to conduct heat and electricity. Because of that, it gets disqualified, because we are looking for that will be able to conduct heat and electricity. Looking at magnesium, categorizing as metal and non-metal, it qualifies to be a metal. As a metal, it automatically then qualifies to be able to conduct heat and electricity. So it is ruled in, leaving out oxygen also as a nanometal, and being a nanometal, automatically nanometals do not conduct heat and electricity. Another question is to do with the chemical symbols. What is the chemical symbol for calcium? Chemical symbol for calcium. We want to get the chemical symbol for calcium. Here we have options. We have C, we have Ca, then Cl, and Cu. A, B, C, and D. So the chemical symbol for calcium. Now this one takes us back to when we were talking about how to assign symbols to elements. There are rules associated with it. We also saw that we have elements that have symbols one letter as one letter, and those that have two letters. Those that have two letters, they must have the first one as a capital letter by size and by appearance, then the second letter as a small letter. The letters should not touch each other as a rule. Now, for us to get which one is calcium, you also need to know what the others mean or stand in for, or symbols for which kind of elements, for you to know which one is calcium. Starting with the A, C. C is a chemical symbol for carbon. So being for carbon, then automatically it is not for calcium. Ca, this one is the chemical symbol for calcium, which must be written correctly, capital letter C, small letter A, and it should not be touching each other. To finish off for the others, this one is chlorine, and this one is copper. Looking at the way I've written, this is wrong. This is not the correct way to write copper. As much as it is Cu, one can easily look out and say, but it is correct. No. The correct way to write this symbol, as I've said, it must be, first letter must be capital. So it must be capital by appearance and by size. Then the small letter, which is the second one, small by size and by appearance. So this one is different from this. You can see C and U are of equal size. This is wrong and this one is correct. Another question to do with the periodic table and something previously covered. Predict, or let's get this one. Which of the following scientists first developed a simple version of the periodic table? You can remember the story of how the periodic table was developed and there's so many scientists that were involved. So out of the list, as we covered earlier, let's predict the correct response of the scientist that was involved in developing the simple table, which is the periodic table. Number one is Dalton. Number two is Leonard. Number three is Mendeleev. Then Thomson. So it's good to know some story about all of this. All these scientists were used in developing some ideas in chemistry. Like Dalton, John Dalton was involved so much in an atom. Leonard, the same. Then Thomson was also involved so much in an atom, and also you remember when we were talking about the kinetic theory of matter, you discovered that all of these scientists were also involved. However, to be very specific on the atom forming that element and being arranged in a sequential manner, though it was simple at that time, the only scientist who managed to do that was Mendeleev. Mendeleev was the one who came up with a simple idea of how the periodic table should be arranged, and he started off by using the mass, which, because of the so many problems he encountered, he couldn't have finished the whole periodic table as we are seeing it today. Some of the problems he faced was masses due to isotopes. You find there are two elements that are having the same mass, but if you check on the number of protons, they are different. Protons are different, but masses are the same. such elements are called isotopes. And having isotopes, without your knowledge, obviously he got a rough time arranging those elements. Not until when James Chadwick came in 1932 to discover a neutron, which now gave a proper light on how mass comes in, so that you discover that these elements that you thought are the same, having the same mass, now disturbing you on how to locate them in the periodic table. The neutron came in to explain that aspect, that neutrons are the ones that are causing the masses to be the same, but they are of different number of protons, changing the aspect of using mass to arrange the elements to using atomic numbers, which is the number of protons. That was so good of Mendeleev. He gave us a direction on how to develop now what we have today. Another question is, predict how many nitrogen atoms will be in a molecule of the compound dinitrogen pentoxide. Now this one is taking us to symbols and formulas. Symbols and formulas. You remember that's the area we covered just before covering the periodic table. So the question is asking, we predict how many atoms will be in a molecule of a compound dinitrogen pentoxide. Now you will find in some areas it will be written pentoxide. It is only an issue of picking part of the name. You remember how we were naming the compounds. The first name is given in full. You can see it is in full, nitrogen. Then the second name, we pick half or part of the name, which we have it as ox here, and we also have ox here. Then we complete by an IDE, which is here, IDE. But in this name, we also have a number to show how many of those elements are present in the formula. So the second element, we are having this or this as an indication of the number. Remember, penta means 5. So you can either have it as penta or pent, still acceptable. Then this one is showing the number of the first element in that compound. So it is asking how many nitrogen atoms will be in a molecule of a compound dinitrogen pentoxide. How many nitrogen atoms? So nitrogen atoms are the ones we are after. The best way to know is by writing the formula from the name. Let's write the formula. We are sure the first element is nitrogen, so nitrogen. It must be in capital form, appearance and size. Then the second element is oxygen. Still capital because they stand in for different elements, so they must all be capital. Now, the first element is a given prefix of a number di. Di stands in for 2. So we have 2 here. Then the second element, which is ox, meaning oxygen, is given a number 5. Pent. So this one gives us the formula of the compound. The formula of the compound. As you can see from the heading, we are now looking at the formula of the compound. But the question is not asking us for the formula. It's asking us for atoms of nitrogen in the formula. And the answer is 2. The answer is 2. So from the predictions we have here, we had 1, 2, 3, and 5. 1, 2, 3, and 5. So you find that A is not the correct response, B is the correct response, 3 is wrong, and 5 is also wrong. 5 is only coming in maybe as a confusing because it will be talking about oxygen and not nitrogen. Another question of similar type is, how many oxygen atoms would you expect to find in a molecule of sulfur trioxide? Sulfur trioxide. They are looking for atoms of oxygen. How many atoms of oxygen can we get in sulfur trioxide? The same way we have handled the dinitrogen pentoxide is how we are going to handle this. So number 1, we write the formula of the compound from the name. The first element is sulfur. The second element is oxygen. How many sulfur are we having? We don't have anything here. Once we don't have anything there, then it means we only have 1 sulfur. If we could be having something like a di, then we could be supposed to put here a 2, tri, 3, penta, or deca 10. For oxygen, we have something here. Tri. Tri means 3. So 3 of oxygen. 3 of oxygen. As you can see the name, sulfur trioxide. So answering the question, the options we have are 1, 2, 3, 4. A, B, C, D. So those are the options we are having. From that, you can see the correct response is C, which is 3 atoms of oxygen. 3 atoms of oxygen. So it is important for you at any single moment to know how to write the formula, because it's out of the formula that you can get anything that you want. Now another question which is in statement form and is good because it will assist us clear some air is as follows. What is the main difference between molecules of elements and compounds? The difference between molecules of elements. Molecules of elements and compounds. What is the difference between molecules of elements and compounds? Remember, they are all compounds. But we need to get the difference between these two so that some other time when you are talking about or you are handling such things, you don't get confused. The first thing we need to know is what is a compound. And a compound is a combination of 2 or more elements. A combination of 2 or more elements that cannot be separated by physical means. If you are to separate, you only separate it by chemical means. But they must be 2 or more elements combined chemically, meaning that they cannot be separated by physical means. But remember, the 2 can be of same element or different elements. Remember that. The 2 elements we are talking about that are being used to give us a compound can be of the same or different elements. It's good to give an example. Same element, I can talk of oxygen. Oxygen atom combine with another oxygen atom to give us an oxygen molecule. This is a compound. Why? Two atoms, even if they are of the same element, but there are two atoms giving us oxygen molecule, which is a compound. Let's look at different elements. I can talk of carbon combining with two oxygen to give me carbon dioxide. Those are two elements, and these are compound. So what is where does the difference come in when you are talking about molecules of elements and compounds? The difference is a molecule of an element must be a compound made of elements, made of atoms of the same element. A molecule is a compound made of atoms that are of the same element. And a good example is the one I've just given out here, which is oxygen gas, nitrogen gas, and so on. There are molecules made of atoms, and the atoms are of the same element. But compounds include those molecules. So a compound is a combination of two or more elements that are chemically combined. So this one is a compound. This one is a compound. This is a molecule, oxygen. Carbon dioxide is also a molecule. But carbon dioxide is not a molecule of an element, because it has carbon and oxygen, which are of two different elements. So they all qualify to be compounds, but they don't all qualify to be molecules of an element. Let's look at the responses and see which one is correct, one at a time, as we qualify or disqualify one. A, molecules of compounds have different atoms, and molecules of elements have identical atoms. I repeat, molecules of compounds have different atoms. Molecules of elements have identical atoms. The statement is correct, but it does not qualify, because it is saying molecules of compounds have different atoms. A compound can be of different atoms or the same atoms. So, as much as it is correct that atoms can be different and it is a compound, but it doesn't hold water, because we also have another one here which is of the same but is also a compound. Let's look at B. Molecules of compounds have identical atoms, and molecules of elements have different atoms. I repeat, molecules of compounds have identical atoms, and molecules of elements have different atoms. The first part have same atoms, correct, but is now denying us this one, which has different atoms. It is even now more wrong on the second part, where it is saying that molecules of elements have different atoms. Like now carbon dioxide or oxide is being taken to be a molecule of an element, which is wrong. So B is even more wrong. C, molecules of compounds have more atoms than molecules of elements. Molecules of compounds have more atoms than molecules of elements. That one is not always true. That molecules of compounds have more atoms than molecules of elements is not true. An example is, if I have a molecule of an element like ozone is written as O3, meaning that it has 3 atoms of oxygen. But I can have a molecule of a compound that is not of the same element, and it has less. For example, carbon monoxide or carbon 2 oxide. Carbon monoxide. It has two different elements, but there are only two atoms. Same element, but three. So which one is more? This one is more than this. So the statement does not hold as supposed. Molecules D, molecules of compounds have fewer atoms than molecules of elements. Molecules of compounds have fewer atoms than molecules of elements. Is it always true? That's not the case, because you can see there's a contradiction. It is asking us that molecules of compounds have fewer atoms than molecules of elements. This one being fewer than this. You can see now this one has more than this. So it is also a contradiction from this. But now, I've gone through all the four responses. There are those that are terribly wrong. But we had two. That is the first one that said that molecules of compounds have different atoms, molecules of elements have identical atoms. Then molecules of compounds have identical atoms, molecules of elements have different atoms. Of the A and B, one is totally very wrong and one is much, much closer. Why the responses that have been given are this way is to give you an idea of not all the responses in all the questions or situations you'll be getting will carry all that you know about the statement. Because what we need to see from the responses should be that molecules of elements should have same type of atoms, while molecules of compounds can have same or different. In addition, you have to include they can be more or less. So to have a response having all those is not easy. They will always give you a fraction so that they gauge or be gauged how much you can interpret and choose one to be the most correct, even if it is missing some aspects. So going by what we have seen, A becomes the correct option, which has told us that molecules of compounds have different atoms, while the molecules of elements have identical atoms. Different atoms, identical atoms is closer. But remember, it is not conclusively right, because we have other cases that can contradict it. Lastly, let's look at this question pertaining writing of symbols. Name each of the chemical compounds in the table. Name each of the chemical compounds in the table. So number one, we have this. We name this. May I give all of them? Then we have SO2. The another one, the last one is can also have this one, because they all stand in for very different things. So let's name this as our last test exercise question. Let's start with the first one. And as we name, we have to remind ourselves of the rules. So in naming these, you look at the number of elements present. You can see 1, 2, 3. Once there are more than 3, you have to ask yourself, do you have a radical in it? Whenever you get more than 2, then ask yourself, do you have a radical in the formula? If yes, like in this case, now we can see this is a radical. Identify the name of the radical. The name here is nitrate. After you have identified the radical as a nitrate, identify the other element, which is now given the symbol K, and this is potassium. Since it is written as the first element, it carries a full name, and a radical is always carrying a full name. So the name here comes out to be potassium, full name, full name of the radical, nitrate. So the full name becomes potassium nitrate. The full name here is potassium nitrate. Full name of radical, full name of the first element. Looking at the second one, this is a gas, an nonmetal, having S and O as the two elements, only two. When we have two elements, the rule is the first element should have full name. The second element will take part of the name, and the remaining part of the name will be filled up by IDE. Again, in addition to the second element, we need to identify the number of the elements forming the second element. And here we are having two of them. So in the name, we have to have the two in it. So the name for the first element is sulfur. The second one is oxygen. We don't take the whole oxygen, but remember there are two of them. So we have to put in how many they are first. That is di. Oxygen, we take ox, then we fill up with the IDE, giving us the name sulfur dioxide. Sulfur, which is sulfur, di to ox, oxygen, IDE, the rule, sulfur dioxide. Second last question. We identify the elements here. Elements we have one, this one and this one, they are standing in for hydrogen, and this one is oxygen. Three elements in it. As I've said, once you get two, more than two, then look for if a radical is present. Indeed, here we have two radicals. This one is a radical, and this one is also a radical. This is a special radical. It is the only positive radical, and this one is a negative radical. Being positive is given the first priority in writing the formula. Let's identify the name. The name for this radical is ammonium. The name for this other radical is hydroxide. So all radicals, all their full name is given. So we have our name as ammonium hydroxide. Ammonium hydroxide, carrying the two radicals separately. All radicals, you give the full name. So the full name hydroxide, the full name ammonium, giving us the name ammonium hydroxide. And lastly, we have NaCl. Let's identify the elements. We only have two, even if the letters are four, but the elements are two, meaning that each element has two letters standing in for the element, by the name sodium and by the name chlorine. Now the rules, the first element is given full name, which is sodium. Second element, you take part of it, chlor. I remember having said that you have to be very careful on which part to choose, because it has to give a realistic name. So we take chlor so that we can now fill in with the IDE, giving us sodium chloride. That is how to get the names of the names of various compounds, and vice versa. You can still get from the name, get the formula, especially for those elements that have those compounds that have only two elements, and for those compounds that have an element and a radical. So we have been reviewing our previous topics in preparation to our next topic, which I'll be handling and introducing in our next lesson. That marks the end of our lesson today. Thank you.